In this video, I want to talk about outliers and the related concepts of influence and leverage. So what do we mean by an outlier? An outlier in the context of regression is a point where the residual is particularly large. So in this slide, we see a very simple example of a linear regression. There are only 6 points, and the regression is estimating a line through those points. And you see that one of those points, the marked blue one, is very far from all the other points. But not only is it far from the other points, it has a very large distance to the regression line. So residuals are the vertical distances in the direction of the y-axis from the regression line to any of these points. And you see that the blue point is much farther from the regression line than any of the other points. And if we had not included this outlier, the regression line would have been where the dotted line is. So an outlier is a point that is far from all the other points in such a way that the residual of the regression is particularly high in this case. Here is an example of another point that is also very far from the other points, but you can see that the regression line goes straight through it. So this point, the blue point here, is far from the other points in the dataset, but the residual is actually particularly large. In fact, it's close to 0. The line goes basically through the blue point. So this is not an outlier, but it is a point that has very high leverage. High leverage is a point that is far from all the other points, that has had a big potential influence on the regression. So it's a point that is in the x direction, far from all the other points. And then finally, in this example, you see another point that is far from the other points. So it still has high leverage because in the x direction, on the x-axis, it's far from the other points. But this time we also call it high influence because it has had a very major impact on the regression line. On the previous slide, the difference between the solid line and the dotted line was relatively small. On this slide, the difference between the solid line and the dotted line is very large. The slope coefficients are very different when we estimate the regression with the blue point and without the blue point. So to quickly recap, an outlier is a point that has high residuals. It is on the y-axis far from the other points. High leverage point is a point that on the x-axis is far from all the other points. And an influential point is a point that is far from all the other points on the x-axis and has had a big impact on the estimate of the beta coefficients. If we had left it out, our estimates would have been very different. So you might remember about standardized variables. This is variables where we subtract the mean and divide by the standard deviation, and that puts a variable kind of on a common scale. Right? So if I measure different things, say I measure my length in meters or in centimeters or in millimeters, I get very different results. But if I look at the average length of a person and how many standard deviations am I away from this average length, then I have put it on a common scale, regardless of how this length was measured. And so similarly, we have this issue that whether a point is far or away from the line or not depends really on how far all the other points were away from that line, what is considered far. And so we need to put them on a common scale, all these residuals. And so to look at whether a residual is far from the regression line, we look at standardized residuals, and more specifically we talk about externally studentized residuals, and I will get to what that means exactly. So before we get there, a little bit of matrix algebra. There's a matrix called the head matrix, and I want to briefly talk to you about what that actually does. And I think it actually helps to generally understand a little bit what linear regression is. We have a higher dimensional space that all the points are placed in. Imagine a space where there is an axis for each of the independent variables. So for the first independent variable there's an x-axis, for the second independent variable there's a second x-axis, so x1, x2, x3. And there's also a y-axis on which we measure the dependent variable. And so every observation in the data set has a particular value on each of the x variables and a particular value on the y variable, and therefore has a particular point in this high dimensional space. So each observation can be seen as a point in this space corresponding to its value on x1, x2, x3 and y, or equivalently as a vector from the origin of this space to that point. We can think of regression as projecting, as a projection of that cloud of points that we have in this high dimensional space onto a subspace, a part of that space that is defined by only the x coordinates, not the y coordinates. So if you look at this graph here, you can see the overall line of a point. So the counting from the left, I guess you could say the second arrow that goes to this point in the top right that is called y. That is the vector that denotes the original data point. So it shows you the score of this point on each x variable and on y. And then when we run a regression and we estimate beta hat and we calculate the predicted value for y hat, which is x times beta hat, then we obtain a different point in the space that is below this. You can see that below the point y, which is y hat, which is a point in the space defined by the x and x axes, not taking into account any deviation, any variation in y that is not part of this subspace defined by x's. So that's a somewhat difficult way to say that a linear regression is really a projection. It's a projection of all the data points into a reduced space that is defined by all the x variables. And the residuals then, is you see here on the top left, is all the variation in y that is left. So that is orthogonal to this space with the x coordinates, and it's the remaining variation. So if we talk about a projection from one space into another, we can have a projection matrix. Yeah, so multiplying a vector with a matrix is a form of projecting. And this we call the hat matrix because it puts a hat on y, so to speak. So we have y, and we calculate the predicted value of this y, which we call y hat, and we call that the y hat matrix. So sometimes it's called the prediction matrix. And you now have enough algebra to actually work out what that matrix looks like, because we know that y hat is x times beta, and we know that beta hat is calculated, that was in the previous lecture, by x prime x inverse x prime y. So multiplying those two, we get x times x prime x inverse x prime y, and we can summarize that by saying this is h. Yeah, so h is another name for this x times x prime x inverse times x, and the variance of the predicted value is the overall variance times this projection matrix. The variance of the residuals is the projection in the remaining space, so it's yi minus this matrix. Now there's something specific about the diagonal of this projection matrix. So we talked in the previous slide about the leverage. The leverage is the amount of influence a particular point potentially has on the regression output. So in some cases we can really see that, which was in this third slide where the blue point really dragged the line away from the original direction. In some cases it does not really materialize, so the point might be very far from all the other points on the x-axis, but exactly on the line, on the regression line as it would have estimated anyway, so it did not influence the results much, but the leverage is still high. And so as a measure of this leverage, we have the diagonal of this projection matrix. If the diagonal of this projection matrix has a high value, then that particular data point has had high leverage, so had a strong influence on the result potentially. So not necessarily an influential point, but a high leverage point. So a high leverage value means that this particular x vector is very far from the overall points in the space in x. I showed you 2 slides ago that the variance of the residuals is sigma squared times I minus the hat matrix. So for an individual observation we can also look at the diagonal, and we can say that the internally studentized residual is the original residual divided by the square root of the variance times 1 minus the the leverage. And so that is related to, you're basically saying we are dividing every residual by its standard deviation, and therefore we are sort of standardizing this function depending on the leverage, right? So because the amount of variance in the residuals depends on the leverage of each point, we have sort of an individual estimate for this variance for each observation, and it's a form of standardization, but not where every residual is divided by the same standard deviation, but where every residual is divided by a calculation, a variance estimate that is based on the head matrix. And then there's also a more complicated externally studentized residuals that makes use of the deleted residual, which is the difference between y and the predicted value of y if for the prediction we had excluded this particular observation. So normally we think of residuals as the difference between y and y hat. So for each observation we look at what is the real observed y and what is the predicted y given our regression. And we look at the difference between those two as the residual. But a deleted residual is a residual where we run the regression separately with each of the observations removed one by one, and then we look at the difference between the observed y and the predicted y for that one observation that was removed if the regression was estimated without including that particular observation. So that gives you a clear idea how much the residuals change, how much the regression line changes because of the one observation. We can work out in detail what then the equation would be of this studentized residual when we, for each of the ith observations, calculate it separately with a residual that is based on a regression excluding that particular observation. Yeah, so this is a measure of how much leverage or how much influence a particular point, how much influence I should say, a particular point has on the regression output. So Cook's distance makes use of both the this externally studentized residuals, right? So in the third equation here you can see this t, which refers to the externally studentized residuals, and then it looks at the variance of y hat and the variance of the residuals. And so basically what you are testing is whether the residuals are radically different when excluding these particular observations each time compared to the overall regression. So if you find a very significant f-test, then these two variance measures, which are sums of squares, chi-square distributions, therefore if you divide you have an f distribution. If that test is significant, they are significantly different, and the particular points that you're looking at will have had a significant impact on the regression. Yeah. Whereas if the two f distributions are very similar, then it did not matter much whether you calculate regular residuals or externally studentized residuals. Right? So if the internally and externally studentized residuals are more or less the same, then leaving out that one observation does not matter much where the regression line is. If the internally and the externally studentized residuals are very different, this f-test will give a significant result, and you can reject the null hypothesis that the regression line is very similar with or without this regression. Or another way to put that is to say that the null hypothesis is that the beta coefficients are pretty much the same with or without this observation. So as Cook describes it himself, you can take this ratio as the relative sensitivity of the estimate to this particular value, and you can see t squared, the squared externally studentized residual, as a measure of the of it being an outlier, this particular observation. Now there's a number of things you might consider when you do encounter outliers. The first, and this is not a joke, is to ignore the problem. Yeah? So what a lot of people do quite quickly is to remove observations that are outliers. So they have a data set, they have a particular theory, they try to test it, they find some cases that are very different from all the other cases, and they get better statistical results if they remove those outlying observations. Now, if I were to try to come up with a reasonable prediction, I run a company and I want to predict consumer behavior, and I'm looking at some data patterns and try to come with a good model that predicts their behavior, I might well apply this strategy. But if I want to come up with a good social science theory and I'm testing this theory, the idea that we just drop a few observations because they don't suit our results is of course more problematic. So I would be more inclined to just ignore the problem and say, well, unfortunately there are outliers, and maybe this is just a fact of life, and maybe they should not change our results. Better though is to look at the second point and try to come up with why they are outliers. Is there something specific about this country that makes it an outlier or a particular case? Quite often it might be some omitted variable. If I, for example, look at development and democracy, I might want to include a dummy variable whether the particular country is an oil state or not. If I don't, my results could be quite different from when I do. And so I might find outliers, cases that are very far from all the other observations, because economic growth is particularly high just because it relies so heavily on oil, which on other indicators then would not be such a highly developed country. And so you get outliers, you get extremely rich countries because they rely on oil, and if you ignore this variable, then maybe you get outliers. So sometimes there's just an explanation why a particular case is an outlier. And then maybe if you have an explanation, it means you are missing a particular variable or a particular interaction and so forth. So perhaps you need to add another variable, or perhaps you need to transform your variable to make it more reasonably aligned with the rest of the data. Sometimes, for example, taking the log can remove outliers. Now, I would not immediately do that. I would think about that carefully too. We get to that later at some point in the course. But it's just an example of where it might help. There is an issue of overfitting. Overfitting means that you keep tweaking the model so that it fits your particular data set at some point perfectly, but it becomes poorer and poorer at fitting any additional data you might add. So it becomes too specific to your data set. It doesn't tell you much anymore about the underlying population. That's always a risk. And finally, there is something called robust regression, which is a regression that adjusts for this for age basically. So it reduces the influence of highly influential points. So we can come up with regression specifications that downweigh the influence outliers have on the results.